Okay. All right. So anybody who is not signed up properly with his or her real name should do so, because the next time I'm not going to warn you. I just would take you off. If you sign up also, you would you sign up, and then how do we call this? You unmute yourself. When you need to ask a question, you raise your hand electronically, and you'll be given opportunity at some point to ask your question. So the using your real name also helps, because then automatically we know who and who are in class, and it can also help with your attendance. So those who are up to evil and want to use funny names and so on, sorry for you. It will catch up with you. I'll take you off and so on. We don't tolerate crap on nonsense on this class. It's a serious business. Okay. So in this particular lesson, we are going to address some of the issues regarding computer system performance. And we're going to begin with the consideration of the need for balanced utilization of computing resources, which provides a perspective that is useful throughout this particular module of this particular course. And so we would look at contemporary computer organization designs intended to provide performance to meet current and projected demand. And finally, we are going to take a look at some of the tools or models that have been developed in the industry to provide a means of assessing the comparative computer system performance, so benchmarking and so on. So some of them not necessarily too useful for you at this time, but for those who would want to pursue further studies or further projects in computer architecture may be useful. But at least we just familiarize ourselves so that we know some of these things exist. So designing for performance, basically year on year on, the cost of computer systems continues to drop dramatically, while the performance and capacity of those systems continue to rise equally dramatically. And so today's laptops have the computing power of yesteryear's IBM mainframe computers or computer. And you can even substitute, instead of saying today's laptop, you can even substitute that for today's smartphones. Because in actual sense, some of today's smartphones are so powerful that could match up with that of the IBM mainframe in yesteryears. For example, Galaxy 21. Is it 20 or 21? One of them. I think 20. It has Ultra and so on with extra power. It has a RAM of about 32 gig and so on, which hitherto were that of powerful computing systems. So if you can now have embedded systems like smartphone that can have comparative power, then obviously there's been a power surge, power in terms of performance. And so we have virtually free encode computer power. Processors are so inexpensive that we now have microprocessors that we can throw away. throw away in terms of like things that we can easily dispose of, and so on. Something that we use like test kit, you use it once, or like disposable razor or something that we use once and throw it away, or use a couple of times and throw it away. So, and this kind of trend is also continuing in terms of technological revolution that has enabled the development of various applications of outstanding complexity and power. For example, the desktop applications that require the great power of today's microprocessor-based systems include image processing, three-dimensional rendering, speech recognition, video conferencing, multimedia offering, and no wonder we have so much magical or something kind of movies because of multimedia authoring. So they can infuse in it things, sometimes even the same person acting multiple roles and seemingly talking to himself and so on. All those come from multimedia authoring and editing and so on. Okay, due to powerful machines that we have. So some of these, we have voice and video annotation of files, simulation, modeling, and so on and so forth. And some workstation systems now support highly sophisticated engineering and scientific applications, and have the capacity to support image and video applications, as we've said. So in addition, businesses are relying on increasingly powerful servers to handle transaction and database processing, and also to support massive client-server networks that have replaced the huge mainframe computers or computer centers of yesteryears. And as well, cloud service providers, CSPs or ASPs, application service providers, as you may call them, or generically ISPs, internet service providers, also use massive high performance banks of servers in order to be able to satisfy their high volume, high transaction rate applications for a broad spectrum of clients that they have, because some of the customers would demand powerful services and complex services and so on, as we saw from Emma Ano. You are scratching my screen. I don't know what you're doing. Please kill it. Clear that. You are scratching my screen. I honestly, wow. Whenever you're having classes, and so like I said, I'm no longer going to complain about anybody. I just remove you. Boom. That's all. Because it's so difficult breaking into class and making unnecessary comments about people who don't care. They are psychopaths. They just have no feeling of pain when they hurt somebody or disorganizes another person. Anyway, let's go on. So in terms of the Intel x86 processors or the IBM mainframe computers, so, there's been mind-boggling in terms of power, the power with which they operate. And it is said that this power has come about as a result of the pursuit of the manufacturers in processor chip development or manufacturing. And so to be able, the evolution of these machines continues to bear out the Gordon Moore's law, as mentioned previously. So long as the law holds, chip makers can unleash a new generation of chipsets almost every 3 years, you know, with capacity in a dynamic, for example, in a dynamic RAM, random access memory, and still the basic technology for computers, mainframe, not mainframe, main exactly. The addition of new circuits and the speed boost that comes from the reduction in the distances between the key components of CPU and the main memory, and also the IO module, has improved the performance in 4 or 5-fold every 3 years. And since trend has continued even up until today. So the raw speed of microprocessors will not achieve its potential unless it is fed with a constant stream of work this type of speed at bay. And that is how come we have techniques or algorithms in contemporary processors that we've listed here. These are aimed at performance. Okay, so like I told you, the ultimate objective of computer architects or of every computer designer is to have or to achieve better performance. So performance is key, either to enhance it or to improve it or to achieve greater performance, whichever way you want, whatever adjective you want to use. So we consider herein these 5, if you like, algorithms. So we have pipelining, and basically when we talk about pipelining, we are referring to the execution of an instruction which involves multiple stages of operation, which looks like the stages of operation or stages of flow of, say, water pipe or traditional pipe. Okay, and it includes fetching of instruction, decoding of the opcode, fetching of operands, and performing a calculation, and so on and so forth. So pipelining basically enables the processor to work simultaneously. So in taking care of these on a multiple instructions by performing different phases of each of these in multiple instructions at the same time. So in this particular case, the processor would overlap some of the operations by moving data or instructions into a conceptual pipe with all stages of the pipe processing simultaneously. So for example, while one instruction is being executed, the computer or the processor would be decoding the next instruction. And this is the same principle as seen in the assembly line. So if you go to a factory, they don't wait till the one process is completely, whilst maybe finishing the product. The raw materials are also being prepared, is already in line, some other stage is being processed or completed, and so on and so forth. So those are pipelining approach or algorithm, as we call it in computing. Then we have branch prediction. Basically, branch prediction, the processor looks ahead in the instruction code that is fetched from memory, and then it predicts which branches or groups of instructions are likely, most likely, to be processed next. So if the processor guesses right most of the time, it can prefetch um, it can prefetch the correct instructions and buffer them so that the processor is kept busy. Mind you, all these ideas started coming because the keyboard, the monitor, the other peripheral devices, and so on are relatively slow. So before the introduction of some of these techniques or algorithms to boost up the performance of the processor typically was idle for most of the time, because if it requested, it's waiting to receive keystrokes from keyboard. So it's just waiting, idle, not doing anything. And that is expensive, expensive, how do we put it? Non-utilization, if there's a word like that, of the processor's time and resources. So computer architects had to find a way. And so that is why so-called pipelining and branch prediction. So branch prediction, so if the system, based on certain instructions that it had executed, can use that to predict and predict it right, then obviously there is marked improvement of the processor's time. So the more sophisticated examples of this strategy predict not just the next branch, but multiple branches ahead. And therefore, the branch prediction increases the amount of work that is available to the processor, okay, to execute. And then we have superscalar execution. Here, the ability is to issue more than one instruction in every processor clock cycle. So in effect, multiple parallel pipelines are being used or utilized. And that is what we call superscalar execution. Then we have data flow analysis. So in data flow analysis, the processor analyzes which instructions are dependent on each other's results or outputs or data in order to be able to create an optimized schedule of the instructions. So in fact, instructions are scheduled to be executed when ready and is independent um, independent of the original program order. And this prevents unnecessary delay. Then last but not the least, we have speculative execution. So speculative execution utilizes branch prediction and data flow analysis algorithms. Like in every computing or technology endeavor, there is always um, advantages, pros and cons to every algorithm or every technique or mechanism. So here, in a similar fashion, the key advantages derived from data flow analysis and branch prediction are enjoined to develop the speculative execution. So some processors speculatively would execute instructions ahead of time or ahead of their actual appearance in the program execution. And then it holds the results in a temporal buffer or accumulator or register. upon the overall experience or processor performance. And so that's what we're talking about. So these 5 are aimed at improving the processor performance or processor speed. Okay. There ought to be a balance. As we've always said, I think I mentioned it previously, that in engineering, there is a perfect machine theoretically. In theory, we call that machine the perpetual motion machine of the first kind. This machine is so perfect, there is absolutely no fault with it. It will never go faulty and so on and so forth. And that's not reality. So it only exists in engineering in theory. So yes, in engineering or in computing, you can design the best performing computer or microprocessor. But without taking other factors into consideration, all you will be doing is that this would never be implemented or can never be implemented because it cannot be achieved in reality. So while processor power has raised ahead at breakneck speed, other critical components of the computing system have not kept pace with it, such as the keyboard, such as the mouse, such as the monitor, and so many others. So the result is there is the need to look for performance balance. So there is the need to make an adjustment of the organization and the architecture in order to be able to compensate for the mismatch amongst the capabilities of the various components that we're dealing with. So the problem created by such mismatches is particularly critical at the interface between the processor and the main memory. So whilst the processor speed has grown between the behind so badly. So the interface between the processor and the main memory is the most crucial pathway in the entire computer system. And because it is responsible for carrying the constant flow of program instructions and data between the main memory or the memory chips and that of the processor chip, if the memory or the pathway fails to keep pace with the processor's insistent demands for data, for instruction, then the processor stalls in a state of waiting or idleness. And so that is what we want to avoid. And then valuable processing time will be lost, or valuable processing resource will be lost. So a system architect can attack this problem, attack this problem in a number of ways, all of which are reflected in contemporary computer designs or systems of today. So here we look at the increase in the number of bits, for example, that are retrieved at one particular time by making the DRAMs, the dynamic RAMs, wider rather than deeper by using wide bus paths. So what we're saying here is just like a typical example I can give you is the street in front of our campus at Tesano. I think it's called J. Kufuor Avenue. If you like, Kumasi in Sawam or Accra, Kumasi or in Sawam, trunk road or highway, whichever. And there are 3 lanes in front of our There are 3 lanes on either side. Now, unfortunately, because of where we come from, in poor Africa, Ghanaian setting, the engineers have put a huge median, and sometimes some of the median could contain even 3 cars. You know, you go on the N1 or some other road. I think the Legon one is a typical one. You get to Legon Medina, you get to some places, or even all throughout 37 to Accra and so on. You get to some of the places, the median alone can take about 3 cars. Crazy. Whereas we could, because it's done elsewhere in the developed world, what they do is that they would make markings, maybe double marking to demarcate. And because they can easily follow rules and regulations, they can easily from Accra towards Nsawam. So in that case, then you can move the cones also back to the other lane facing Accra. And by so doing, you could create 4 or 5 lanes, because the traffic that is flowing to the other end is minimal. And so even if it was only 1 lane, the traffic will flow without any congestion. And typically, so that is what we do. Well, the computer architect has designed the dynamic ramps so that it has wider path to be able to transfer the data instruction that is needed. Now, another approach is to reduce the frequency of memory access by incorporating increasingly complex and efficient cache structures between the processor and the main memory. And this we had already alluded to when we talked about, when I showed you the processors, the evolution with Intel Pentium by Pentium, or I think even X486, we had introduced a cache. So this is the cache. It's set between the main memory and the processor. And even now in contemporary processor designs, the cache system, different levels of cache systems are embedded with the chipset, the processor chipset. And therefore, so when it needs information, it can quickly pick it up without, and therefore minimizing the frequency with which it goes to the main memory, which is slow. So the cache, we will talk about, there's a whole lesson dedicated to cache. The cache is made of a special semiconductor, silicon, that is a bit expensive and is faster. And so it's also smaller in size relative to the main memory. So one of the things that we need to deal with is along the line is, how do we replace or clear the cache? Yesterday, somebody was relating it with her clearing her cache history on her browsing. So that the idea, it's similar to that of computer architect or architecture in organization. But there's the slight difference in terms of the browsing. You, the user, would be physically, or not physically, I mean logically, or go into your computer and clear it. But in terms of the computer processor, the system has designed a number of algorithms, about 4 algorithms, that deals with it. And one of them is least frequently used, LFU. So if there's a data that is being stored or cached in the cache for a long time and it hasn't been used, so at some point the system would invoke that algorithm of LFU, least frequently used, and kick that data out, clear that data from memory, so that it can make space for new data from main memory. Mind you, relative to the cache, relative to main memory is very small. So if every data that it picks from main memory has to make a copy, it won't be long, then the cache itself will be full. And if it's full and it doesn't have any means of clearing itself to make room, then we are back to square one, where the processor, when it needs any information, would have to make the request to the main memory, which is the old system, and therefore there will be no use having the cache system. But there is good use of having the cache system, and that is explained in the fact that there are different algorithms to take care of that. And then there's also the change with regards to the DRAM interface to make it more efficient by including a cache or other buffering scheme on board the DRAM chip. So the same concept that we employed in the main processor has also now been employed in the DRAM, the dynamic random access memory. And then there is also the increase in the interconnect bandwidth between the processors and the main by using um, by using by using I had to remove somebody, some rude person disturbing us, some evil disturbance. Okay, so never mind. So the between the processor, the bandwidth between the processor is increased by using higher speed buses and a hierarchy of buses to buffer the structure. So this is also similar to the vehicular example that I gave when you expand the bus lanes. Okay, we would also talk about actual buses as peripherals along the line. So this diagram, take a good look at it and see the speed with which some of these peripherals are. So from keyboard, mouse, scanner, and so on and so forth. So just take a minute to familiarize yourself. Okay. So as the computer become faster and more capable, more sophisticated applications are being developed that support the use of peripherals with intensive I/O demands and so on. And so this figure gives us some of the examples of some typical devices, I/O peripherals that we can familiarize ourselves with for personal computers and workstations. And so some of these devices create tremendous data throughput demands. And so while the current generation of processors can handle the data pumped out by these devices, there remains the problem of getting the data moved between the processor and the peripherals in terms of speed. And so different strategies are usually put forth or developed, including caching and buffering schemes, plus the use of higher speed interconnection buses, so that more elaborate structures of buses could facilitate the movement of the of the data. So what we're saying, if you compare this with uh, the vehicular traffic, you could think of a highway like Temamoto Way, even though now it's been encroached to the extent that if you're speeding on Temamoto Way, Accra Temamoto Way, you still ought to be careful because human beings and sometimes animals are crossing constantly. But typically, you know, it's unfortunate that the Ghanaian example usually is not a good example, because typically if you call something highway or motorway, nobody crosses it. It's usually even guarded. So they would raise um, um, some structures on the sides to guard it. So you are 100% sure that nothing is going to cross your pathway, and so you could speed at the highest permissible speed, and be able to achieve your goal or your target of of using the motorway. And that's the reason why we pay toll for it. So you pay for it. If you don't want to pay for it, you go and use the regular one that would give you number of stops and so on. Okay. Okay. So improvements in chip organization and architecture. So as designers wrestle with the challenge of balancing the processor performance with um, the that of the main memory and other computer components, there is the need to increase the processor speed, which remains at the heart of the computer architect. And there are three approaches to achieving this increased speed. First, the increase is to increase the hardware speed of the processor. So this increase is fundamentally due to the shrinking in size of the logic gates of the processor chip, so that more gates can be packed together more tightly, and also to increase the clock rate. With the gates closer together, the propagation time for signals is also significantly reduced, which enables the speeding up of the processor. So an increase in the clock rate means that individual operations can now be executed more rapidly, because the execution usually occurs within the clock rate. Okay, that is how the processor is judged. So within a clock cycle, how many additions, for example, can be made? So if we compare that with the very first computer, ENIAC, electronic numerical integrated and computer, it could only do 18 additions per second. And then we saw about 40,000 additions or operations per second with the EGVAC, and with the second generation, and so on and so forth. And today we could do millions, perform millions of operations per second. Okay, so the next is increase the size and speed of the caches that are intersposed between the processor and the main memory, and in particular by dedicating a portion of the processor chipset itself to the cache. And so that has brought in marked improvements. So the cache access time significantly drops, because now the processor and the chip are all on board the same chipset. So if there is the need to get any information, it is not going to go to any particular, it doesn't require the system bus per se because it's on board. And then another part is also to dedicate, to split the chipset, the cache, to split the cache as we saw in the examples that we've seen before. So then we have L1 being part of it dedicated to instruction, and L1 data dedicated to only data. And the same with L2, level 2 cache dedicated to instruction, level 2 cache dedicated to data. And so once these strategies are put in place and is on board the processor chipset, so it improves the speed with which this is made. Another one is making changes to the processor organization and the architecture such that the increase, it increases the effective speed of the instruction execution. Typically, this involves using parallelism in one form or the other. So the idea of pipelining, being able to process it in a simultaneous parallel manner, is achieved herein. So problems associated also with clock speed and logic density. Not logging, logic density, maybe. I think I should change it. Anyway, so traditionally, the dominant factor in performance gains has been with the clock speed and then also logic density. Now, the clock speed and the logic density, as they increase, the number of obstacles also become more and more significant. So how do we deal with this? So there are a number of ways. One of them is power, with regards to the power. So as the density of the logic and the clock speed on the chip increase, so does the power density. So the difficulty of dissipating the heat that is generated due to the high density, high speed chips is also becoming a serious design concern or issue that ought to be addressed. And then also there is the resistance and capacitance delay, RC delay. So here, the speed at which the electrons can flow on a chip between transistors is limited by the resistance and the capacitance of the metal wires that are interconnecting them, or these components. And specifically, the delay increases as the RC product increases. So as more and more components are added on chip, there is definitely, with regards to the chip decrease in size, the wire that interconnects become thinner, and thereby also increases the resistance. And the closer they are together, also would increase the capacitance. And so we have to have a trade-off between this. Then we also look at the memory latency. Latency is the terminology for delay, time delay in computing or in technology. So here, memory speeds lag the processor. This is given, we know that already. So there will be the need for more emphasis on organization and architectural approaches to improving the performance of these techniques, some of which will be discussed as we go on. Okay. So those of you disturbing, please be warned. I can't say it more. When you sign up, please. Okay. Whilst I'm even warning him, he's blowing some evil thoughts out. I can't get it. I think for now, I'm not going to, I keep saying, but sometimes I feel, you know, I should still warn somebody just in case maybe this is the first time the person is signing up, you know, but this is common sense. You should know. You go to class late or you go to church late and then you are dragging chairs or dragging your feet. Are you evil or what? Or psychopath? Because you know there are other people there. So if you respect yourself and respect your neighbors, you will not disturb. But constantly we get people disturbing us. And then I have to stop the lesson and then address this evil issue. Okay. Now this chart actually depicts the evolution or the trend of processors vis-a-vis the speed as given in frequency and the power and the number of cores that are put on the processor. So you could see some of the trend, looking at some of the strategies that have been put forward to increase the performance of our systems. So one of the key things that have been done, we have talked about the cache, the increase in the cache capacity, and also the cache being placed between the processor and the main memory, and also the fact that we can even have the cache on board and the number of caches on board the processor itself, which have also improved even the cache speed, access speed, and so on. So, for example, the Pentium chipset was devoted to devoted about 10% of its onboard area, onboard the chip area, to caches. And so contemporary chips devote over half of the chip area to caches now, because now instead of the very first Pentium that had only level 1, now it has level 1 and 2 on board the chip, the processor chip. And not only that, it is also split into instruction and data. Instruction level 2, instruction level, data level 2. Okay, so it means it requires more space. And then a typical, sometimes 3/4 of the other half of the pipeline related control and buffering is also used. And so you could see how the trend goes. So you could see also that in respect of the power, at some point, it saturates, okay? It plateaus or saturates. And therefore, you have to have other mechanisms or in place to be able to have a change. Now we take a look at the multi-core again. So with all of the difficulties cited in the preceding slides in mind, the designers have to turn to some fundamental new approach aimed at improving the performance or enhancing the performance by placing multiple processors on the same chip with large shared cache system as well. And so the use of multiple processors on the same chip, also referred to multiple cores, is what we call or refer to as multi-core. Multiple core or multi-core. I mean, multiple cores or multi-core. And it provides the potential to increase the performance without necessarily increasing the clock rate. And studies have also shown that
inside it gets some foam like that.
Mr. Appiaje I'm going to note your name. You're going to be out of the class, okay? I don't know where these evil people come from. My goodness. Class rep, you need to talk to your people. You know, I understand we have some psychopaths amongst us. So no matter what you do, they won't budge. But hey, you have to bring common sense to bear. I mean, we are having class, you just jump in and start talking and creating noise. The class is not compulsory, like I keep saying. You don't need to be here. Please. Anyway, so some studies have indicated that within the processor, there is the increase in performance, which is roughly proportional to the square root of the increase in complexity. So in other words, as the performance increases, there's also some marked increase in complexity of the system that we are dealing with. And that has its own issues. So for example, if the software can support the effective use of multiple processors, then doubling the number of processors almost doubles the performance. And that's the strategy that we use I think I still need to continue writing down some of the students, especially those who come and disturb us. And then at the end of the semester, they will go and mark their own script without saying anything to them. So if I mean, because it's so disheartening that every minute some evil person will come and disturb us. Psychopaths. Okay. So the strategy is to use two simpler processors on the chip rather than one more complex processor. And that is what lends itself in the Core Duo or Core 2 processors. So with two processors and larger caches are justified. So this is important because the power consumption on the memory logic on the chip is much less than that of the processing logic. So as the logic density on the chips continue to rise, the trend to both more cores and more caches on a single chip would also continue. And two-core chips were quickly followed by four-core chips, then 8, then 16, and so on and so forth. So as the caches become larger relatively, it made performance sense to create 2 and then even 3 levels and so on. And when we talk about the caches, I'll show you a chart that saturates after the 3rd level. And so that is how come practically all our machines have only up to level 3. But theoretically, you could have level 5 or 6 caches. Okay. Then we have many integrated core MIC and incorporated with graphics processing unit GPU. So here the chip manufacturers are now looking into the ways by which they could leapfrog with the number of cores per chip, with more than 50 cores per chip being produced. So the leap in performance as well as the challenges in developing software to be able to exploit some of these large number of cores have also been of a concern to chip manufacturers. So this led to the introduction of a new term called many integrated core, MIC, many integrated cores. So the multi-core and the MIC strategy involves homogeneous collection of general purpose processors on a single chipset. And at the same time, the chip manufacturers are pursuing another design option in which a chip with multiple general purpose processors plus graphics processing units and specialized cores for video processing, for example, and other tasks are being made. So in a nutshell, or in broad terms, the GPU is a core designed to perform parallel operations on graphics data. Okay, so traditionally, the graphics were found to be plug-in kind of graphics card, which was used to encode and render 2D and 3D graphics, as well as processing of videos. But now, since the GPU perform parallel operations on multiple sets of data, they are increasingly being used as a vector processors for a variety of applications that require repeated computations, and then also that of video and so on, video and so on. So in a nutshell, a broad range of applications are supported now by a processor. And so when these are fused together, it is called general purpose computing on GPUs. So they call it GPU, and so on. So again, there are some of these concepts we need to understand or appreciate. So there's also for computer architects to look into ways of improving the system performance. There has been a number of theories and laws and principles, if you like, or frameworks that explains or lend hand to some of these. Examples include the use of parallel processors, the use of memory cache hierarchy, and speeding up of the memory access time and the I/O transfer rate due to technology improvements. And so in all of these cases, it is important to note that a speed up in one aspect of the technology or design does not necessarily result in the corresponding improvement in performance. And this limitation is vividly or succinctly expressed by Amdahl's law. So that is the essence of this law that we are looking at, or principle. So Amdahl's law was first proposed by Jean Amdahl in 1967, and it deals with the potential speed up of a program using multiple processors compared to a single processor. Nevertheless, Amdahl's law illustrates the problems facing industry in the development of multi-core machines with an ever-growing number of cores. As you can see, we started with just 2, increase it to 8, 4, 16, and so on and so forth, 4, 6, 8, and so on. And so the software that runs on such machines must be adapted to a highly parallel execution environment in order to be able to exploit the power of the parallel processing. Again, Amdahl's law can be generalized to evaluate any design or technical improvement in a computer system. And we will take another look at another one, Little's law. So here again, Little's law is a fundamental and simple relationship with broad applications in mind. And we can apply it to almost any system that is statistically in steady state. and in which there is no leakage. So again, it lends itself to more theoretical, because in practice there would be some leakage, if you like. I mean, the fact that even when the system is powered, after a while it heats up. So the electrical energy that you've put into your phone, or even using your battery, with time then it heats up, because not all the energy is converted into, say, light energy to light up your phone or your machine for you and to receive the translation of the data and so on and so forth. Not all of them. Some of them get lost by way of heat. So when the system heats up, those energy is being lost. Of course, I mean, technically, if you look at it from conservation of energy, the theory of conservation of energy, energy can neither be created nor lost. So it's not lost in that sense. But yes, it can be accounted for that it was converted to another form of energy in heat. But technically speaking, this is a leakage, or this is a loss of a sort. Okay. So again, using the queuing theory, if the server is idle, an item that is served or requested would be immediately served. Otherwise, it has to join a queue. When I was talking to the other classes about this, I always would cite an example of a Ghanaian setting where we cannot associate ourselves with queues, lines, because in our Ghanaian context, we've been trained, maybe by way of our education, to be more microwave oriented than any other person, or even than the white folks or those in the developed world who brought us the microwave oven. We want it fast, but we will never get up on time to go to where we're supposed to go. But when we get there, they should allow us alone. We see it in traffic every day. All you need is just the boldness to drive on the other side, or to make noise. Put on your siren or something, and then you make noise. These are things that are not done in any developed world. Anyways, so there can be a single queue for a single server, or a multiple servers, or multiple queues with one being for each of the multiple servers. So a number of strategies are designed to cater for this. And then an average number of items in a queuing system would normally be equal to the average rate at which the items arrive, multiplied by the waiting time. Okay, the time that it spends on the system. So that's the waiting time. So that is what gives the idea, or this is what Little's law is talking about. Again, there are some of these that are for purposes of those of us who would be needing it for further development or study and so on. So this block diagram, or this diagram, is actually showing the system clock, and is depicting the fact that the clock is made of quartz crystal. Now it gives out, or it gives us an output of sine wave or sinusoidal curve. And this sine wave is received by A to D converters, analog to digital converter, which would transform this into pulses. Okay, so it transforms this into pulse for the clock. So the operations performed by the processor, such as fetching an instruction, decoding an instruction, or performing an arithmetic operation, and so on, are all governed by this clock cycle. So they are done within a particular clock cycle, and that is how come we can state that the processor is performing efficiently, because if it has been designed to perform say 18,000 additions per second, we would be able to benchmark and see, is it performing optimally at 18,000 instructions or additions per second, or is it performing only 16,000 within a second, within the particular clock cycle? So this is the idea behind. So typically all these operations begin with the pulse of the clock, and that's the most fundamental level. At the most fundamental level, the speed of the processor is dictated by the pulse frequency that is produced by the clock, and it's measured in cycles per second, or hertz. And so that is why, of course, the equation is also there to support us, the fact that the frequency in hertz is given as a reciprocal of the time in seconds. Okay, time per second, so the cycles per second. So that's why it's a reciprocal. So typically the clock signals are generated, like I said, by the quartz crystal in a sine wave while power is applied. And the wave is converted into a digital voltage pulse stream, which is provided in a constant flow to the processor circuitry. So for example, 1 gigahertz processor receives 1 billion pulses per second. And so the rate of pulses is known as the clock rate, or clock tick, or clock speed. Okay, so this is how the execution or the operations of the computer are done within each cycle. Okay. Okay, so this table is a matrix which shows on one dimension 5 performance factors, and on the other 4 system attributes. And so when we have an X there, it is indicative of the system attribute that affects the particular performance criteria or factor. So again, I'm not going to go much in details of this. These could be used into some calculations, and for this particular course, we will not go into those calculations. It's beyond this class, so we will leave it at that. Okay, so calculating the mean, again, using those parameters, we could calculate any of these 3 means, either arithmetic mean, geometric mean, or harmonic mean. The arithmetic mean, I think that we should be able to calculate, even though I'm not going to demand that. Basically, the arithmetic mean is simple. It's a more appropriate measure if the sum of all the measurements is a meaningful and interesting value. And the arithmetic mean is a good candidate for comparing the execution time performance of several systems. Okay, there are other measures or metrics that would require of this. But again, like I said, I'm not going to demand that of you, so it's something we can skip. Now we take a look at what we call benchmark principles. This is in dealing with the performance. So there are a number of measures such as the MIPS, millions of instructions per second, or MFLOPS, millions, MFLOPS for what's the full? Okay, I'll get to it. For the MFLOPS have proven inadequate in evaluating, I think, let me see. Uh-oh. Am I going somewhere? Okay, this is where we're supposed to be. So where was I? Okay. Yeah. So they are inadequate in evaluating the performance of the processes. And because of the differences in the instruction set, the instruction execution rate is not a valid means of comparing the performance of different architectures, for example. So another consideration is that the performance of a given processor on a given program may not necessarily be useful in determining how that processor would perform on a very different type of application, for example. So accordingly, somewhere in the late 80s and early 90s, industry and academic interest groups started shifting the measurement of performance of systems and using what has come to be known as the benchmark principles. So this same set of programs can now be run on different machines, and then the execution times are compared using the benchmark principles. So it is written in a high level language as against the low level languages of machine language and assembly language and so on. But this is high level, so almost everybody, it lends itself in much utilization because the assembly language are chipset specific. In other words, if you are using a particular Motorola chipset, or you're using a Hitachi, or you're using an Intel, or any other device or microprocessor, for example, then you need to learn specifically the syntax and yeah, the syntax and the code words and so on from that particular manufacturer. So it makes it difficult. So unless you are in that industry and you are using a particular, let's say you are in Intel industry, so then you can easily learn because then the syntax is going to be the same whether it's as a 386 or 486 or Pentium or any of the cores. Then I mean, even if there's change, the change is just minimal. Okay, but the high level is easy to make changes and then adapt. It is also representative of a particular kind of programming domain or paradigm, such as systems programming, numerical programming, and commercial programming. And it can also be measured easily, and it has wide um, distribution. So this is the benchmark. Okay. Uh-oh. Somebody is saying my mic. No, somebody was saying Mills. My mic is not mute. Enoch, can you hear me?
Yes, I can hear you.
Okay, so I suppose the rest can hear me. So if Mills cannot hear, then he has an issue. I think usually try and check with your colleagues rather than sending a chat to everybody and then it interrupts with the flow and so on. Please. Okay.
Yes, sir.
All right. So there's also the System Performance Evaluation Corporation. This is another which uses the benchmark suite. Okay. So I'm not going to bother you so much. For those of us who will be needing it in future, can read more on that. So this is a common need within the industry and academia and researchers on how to measure the performance of the processor in evaluating different ones with different applications and so on. So one of the ways is using the spec, which is an industry consortium that was formed to deal with it. There's Kobina, you are scratching my screen. I don't know what I actually need to learn what you people do in order to scratch the screen. I don't know. Okay, so this gives out some specific spec um, benchmark suite that they call CPU 2006. It's a kind of standard for the processor intensive applications to be able to um, measure um, the performance of the applications and spend most of their time doing some computations rather than um, just checking on the mere performance or the speed. Okay, so again, those ones I can skip, and then these are some of the documentation. I guess that brings us to the end. Like I said, today's lesson or this week's lesson is just a brief one, but I've posted another notes, which is from the old version of the book, our textbook. So please take time to read and familiarize yourself also with that, because that had some other information that is not in this one, and I don't want us to miss it. So yes, sometimes some of the improvements, this is latest that we have adopted, but some of the things you see that I'm skipping, some of them are for certain group of people per se. You know, I'm not going to be asking you about some of these things. So I don't see why I should spend more time on it. Those that will spend time, we would are necessary for us. You will see me spend more time on it. I think next week, the lesson from chapter 3, we will take more look at, because at the end of chapter 3, we should be able to behave like computers. In other words, we should be able to go inside our very own computers and see the working of it, not physically opening it, but logically. After that lesson, when you are working on anything, you would have the mind of going within the abstraction, and then you can really interpret, or with your mind's eye, you will know what is going on within your computer. Okay, now the floor is open for any questions, comments, contributions, and what have you. Yes, please raise your hand. You'll be given opportunity to ask your question or make your contribution. Anyone? Anyone with a question, comment, contribution? Or should I call on names? Those of you also who use maybe your real name, but put only first name or something, please, anytime you sign up, or maybe the account you're signing up from doesn't belong to you, anytime you sign up to the class, you can touch on more under your name and then do a rename. So then you type your full name. You never know, because the system, as is being recorded, we in one day there may be the need. Let's say with the COVID situation, anything could happen. Let's say if we are not supposed to take exams, then how do we evaluate? How do we know somebody came, iPhone came to class, evil iPhone? How would we know who that evil person is? So we wouldn't know. And we are not going to struggle ourselves to find out. So for your own good, have your real names, okay? Unless you are thinking of bad things. If you don't have any ill intent, I don't see why you cannot sign up with your real names. Okay, Do we have anyone who has a question or comment or contribution or anything? Okay, we see Kelvin.
Hello, sir. Please, I wanted to ask that you see that we have some processors that have one core and two logical processors. So I wanted to know, is it a multi-core or a single core processor?
The moment you have multiple cores, is a multi-core. That's the definition of multi-core.
Okay, so I wanted to
Multiple
know,
cores.
is it that we have the logical, is it that we have a difference between the core and the logical processor?
No, logic is the way the operations is done. The computing process, the data processing, is either arithmetic, simple additions, or logic. Logic as in the gates. So if A and B, so if you supply A and B, if it's an AND gate, then when you give the input, what do you get? Of course, we know from previous life or from discrete structures class. So you know how to construct the truth table. So that output is also fed into another gate and so on and so forth. So there's in order to create the processor, there are thousands, millions of these gates that are put together. So normally it would have been a complicated circuitry. So these are put together for us as the processor. And so that is what the processors are made of.
Okay,
that we
sir.
tend to call them microprocessors. So today we have multiple cores. When we started, we had just a single, at that time we didn't call it core, just a single processor. But as we started putting more processors on one chip as one CPU, then we called it multiple core or multiple processors.
Okay, sir.
I hope that answers your question, Kelvin.
Yes, sir.
Or clarifies it. Okay, Alfred.
Hello, sir. Sir, please, my question is, does
When you are
Apple...
given the opportunity, please go ahead with your question. Hello, sir. Good afternoon. Good morning. You don't add up. You won't get any extra mark for that. Anyway, go ahead.
Sir, please, my question is, does Apple use Intel chips?
To be honest, I need to check, but it's possible because the chip is just the processor, but and so that and the the OS is different. So it's the OS that is different. I think so. I need to check. Maybe I don't have, well, I have an iPad, but I haven't checked what sort of processor it has. But
Okay,
I'll
sir.
check.
Okay,
But
sir.
I think it does.
Okay, sir.
Yes.
Thank you very much.
I think it does because Intel is most popular and efficient, and it has a lot of the what do we call it? A lot of the improvements that we have. So that one is just the chip. It has nothing to do with the OS.
Okay, sir.
Yeah. So it's just like yeah, I think it does. Except that I don't have a MacBook to see the Intel inside, but I think it does.
Okay, sir.
Kevin, is your hand up?
Yes, I wanted to add a contribution to what he asked.
Yes.
So it does, but just recently they've created their own, that's the M1 chip. It is called M1 chip, but they also use Intel chip and other thing. But just recently that they created theirs, that's the M1.
Yeah. Okay. Good. Good point. Any other question, contribution, comment? Yes, Hope.
Yes, what I want to ask is that during the branch prediction, does it depends on the constant uh, of former operations to be able to predict operation that is about to be used?
Hope, speak a bit louder. I lost some of the things you were saying.
Yeah, what I was trying to ask is that during the branch prediction,
Yes.
does it depend solely on the constant usage, or I mean, when you constantly use an operation, does it does it store it somewhere and then later on when it wants to predict depends on the former operations that you have done to be able to predict what is going to happen next?
Yes, it has maybe not constant. I won't put the word constant there, but
Okay.
previous instruction. That's what it said. So once a particular instruction has been executed, so the processor is able to look into the trend of the execution of those programs that were, those instructions that were being executed. And then it will be able to make a prediction. It's just like you look at certain behaviors. And so you guesstimate that looking at the line of question from these students, the next question is going to be like this. So you go ahead to preempt that question. So if the algorithm has to be of high accuracy, in computing, we talk about minimal false positives, okay? So, or false negatives. So the prediction ought not to be negative. So you predicted that this instruction is going to be executed and then you prepare for it. Oh, that's not it. So what the branch prediction does is it studies the trend of the instructions that are being executed. Now, instead of following on the program and see that, okay, so once this was executed, this was also going to be executed, it is able to make its own judgment. And then it goes now to tackle certain instructions and get them ready. And most often than not, it has high rate of success, you know. So then it is, and once it has that success, it means that the processor now is more efficient because then the processor is busy, it's constantly busy, rather than it being idle waiting for one instruction to be completed before it starts working on the other. That would make the processor time not fully utilized, and therefore the processor becomes idle and it's expensive, so to speak. So that's about the branch prediction. I hope it is okay.
Yes, I'm answered.
Okay, great.
Secondly,
Yes,
I
go
would like to
ahead.
place what's the main purpose of the logic density?
The logic density.
Yes, please.
No,
I
the
think
logic density is as we add more and more gates.
okay.
So we increase the logic with which, because the logic is also contributing to the processor speed. So we said that we are piling up a number of gates per chip. So technology has helped us to the extent that incidentally, the chip size, physical size, is reducing. Okay, so whilst even is reducing, its power is increasing. And then if you check the number of transistors vis-a-vis the number of gates that are being put on, because the gates are made of transistors, okay? It's transistors that were put together to be able to fire to, so when we talk about, how do we call this? The AND gate that I was referring to, it's actually a combination of a couple of transistors. So you put it here, and then the signal, and then it's able to trigger and so on, and give an output and so on. So that's how the gates are made. So that is how come even up to now we still talk about the number of transistors when actually we are referring to the number of gates. So the density is actually referring in reference to the number of gates, or vis-a-vis the number of transistors as we pile up, but the size is still reducing, and then it has a different consequence. Okay, is it Ann Karen or Anna Karen?
Please, Anne Karen. Sir, I didn't get
Ann
the
Karen,
laws
okay.
you talked about.
You didn't get.
The laws.
Okay, don't worry too much about the laws, but Amdahl's law and Little's law, what they sought to do is with regards to the explaining the limitations with regards to the performance. So from theoretical perspective, they argue from different perspectives as to some of the things that ought to be in place in order to have performance measured. And that is how come after that, we then came to the benchmark principle. The benchmark principle is more generic. So that rather is being used instead of homing on either Amdahl's or Little's laws. But what I added is that these are just for purposes of information. Don't worry too much, because I'm not going to ask you any question on them. It's for those of us who in future may do either research or some programs in computer architecture. They may go deeper into some of these theory to argue it out and so on. Why are you applying benchmark instead of Little's law limitation? Are you, or Amdahl's and so on and so forth? But those are more theoretical that I won't worry you about it. But yes, you can read more about it. Okay, any more comments, question? Maybe you can take one or two more. Yes, Patrick. Yes, Patrick. Patrick raises his hand, you call him, and maybe he's not by his phone, his machine. Okay, we are not hearing him. Oh, he's not unmuting himself. So can we get someone else if there's any?
Sure.
Wow, Patrick, what were you doing? We asked you,
Sorry.
come on, and
Yeah,
yet
what?
Okay, go ahead.
Sorry for that. The stages of the pipelining. The stages of the pipelining. What are the stages?
The stages are akin to how pipe flows in terms of pressure. Okay. So you see how if a pipe is flowing, depending on the level, so it may flow faster, it may much stronger, and so on. So that is the principle behind the pipelining.
Okay.
So when we talk about those stages so the processor would take a look at various stages in the execution. It has to fetch first. Okay, before any execution takes place, it fetches. And we will find out it's when we talk about execution and no execution cycle. When we talk about instruction cycle actually involves multiple stages. It involves the fetch cycle, and in simple terms, then it concludes with the actual execution cycle. That's how instruction cycle is.
Okay.
At some material point, we would add when we enable interrupts, then there would be the fetch cycle, then the execution cycle, and then the interrupt cycle. In other words, after the completion of a particular instruction, the instruction will not be deemed complete until the system checks, is there any interrupt request? If there is, it will deal with that like a loop back or a feedback. And so then that interrupt request is now going to be fetched within the fetch cycle and then executed within the execution cycle. And then it goes back to check again on the interrupt and so on and so forth. So that becomes, redefines the instruction cycle for us. So when we talk about the stages, that's what we mean. I hope it's clear.
Yes, sir. Thanks.
Patrick, is it clear?
Yes, sir. Yes, sir. It's clear.
Okay, so any
It's
other
clear.
question,
Thanks.
or else we will call it another day. It's 10:30. Any other? Okay, if there's no other question, then I'll see you guys, God willing, next week. So